So with that, I would hand over to Aryan, who would talk about the characteristics and capabilities of GenAI for science.
Thanks, Anuj. Good morning, everyone. So I'll talk about some recent frontiers of generative AI and also how scientific knowledge has already been very influential in developing domain-specific generative AI models and how we can use these models for other scientific applications, and really how science and engineering enable a very rich set of problems for AI development. And yeah, so let's start. So there is a bunch of generative models, Gen AI models that we hear about, but roughly a majority of them, you can simply think of them as this big picture, right? As Anuj pointed out, we are learning distributions of data, right? So you can think of them, we are trying to learn this transformation from some easy to sample distribution, like the Gaussian, to this data distribution, like distribution over images, molecules, proteins, right? And this picture in mind will help us understand why some of the models, the family of models which are very popular today, how do they come about? And that is why I'm going to focus a lot of my discussion today on diffusion models, but there are other family of models and they have their own characteristics. But really, the precursors to diffusion models like VAEs and GANs try to solve this problem of this transformation in a single short manner, which means the neural network tries in just one single forward pass, try to generate these samples from the data distribution, which, as you can imagine now, of course, with the power of hindsight, we know that this can be quite challenging, and it led to low quality samples. Right? And the first thing that we want with generative modeling, at least, is we should be able to get high quality samples from our data. And diffusion models work, and they're so powerful, really because they reduce this problem of learning this challenging transformation into a sequence of simpler problems. And that is the big idea about diffusion models, which is iterative refinement. If you remember one thing about diffusion models, that's what you should remember today, right? How they are described, I think this is probably a lot of you have seen this already, but the picture is that for training diffusion models, what we do is we take our data samples, we pick some noise distribution, let's say a Gaussian, and it's very easy to understand in terms of images, right? We take a noise distribution like Gaussian, we corrupt our data under different noise levels, and this is called the forward pass, which is specified by us. And the neural network is trained with this objective to remove this noise that is added at each step. And this is which we call the reverse process, right? And roughly, it's most intuitive to see this in terms of images, but the idea remains same for other types of domains as well, where we're trying to take our original data sample and corrupting it with some form of noise. And then my neural network job is to try to remove that, right? And this gives away to all of us, right? The task of the neural network now becomes is this denoising task, right? And this is why diffusion model, this is the idea about iterative refinement, that now we have converted this problem of generation into this relatively simpler task of supervised regression, right? Which we know how to do, which is denoising in this case, right? And diffusion models, and was alluded to by Anuj earlier, and broadly generative models. So if you read around 2014 and 15, when AlexNet has come around, people are realizing deep learning is very powerful, but we require lots of labeled samples. So unsupervised learning was this open problem in front of the field. And really, diffusion models and generative models, one of the big goals people always had, that this will enable self-supervised learning or unsupervised learning, right? And this is one of the big reasons that they were always looked at. Of course, now generating samples, right, images and text, is one of the other big goals as well, right? So this is how we train a diffusion model. How do we generate samples? After you train it, you sample from this easy to sample distribution Gaussian, and you apply your neural network, your denoising procedure in a sequence of steps, and you'll get your sample from the data distribution, right? But why does this work, right? I think what is the fundamental perspective? Why applying this sequence of denoising operations takes me to this data distribution? And really, one perspective behind this is that this denoising operation that is learned by the neural network is directly related to the notion of a score function. So think about, and maybe I think this slide is the best way to think about it. So if you think about this picture as the space of my data, which includes my actual naturally looking data, but also noise samples, right? And if I am at any particular location, the score function tells me in which direction should I go such that the probability of getting towards the natural data increases the more. And that's the definition, gradient of the log probability, right? So it turns out that this denoiser that we are learning is directly related to the empirical score function at any of these locations. So that is why applying this sequence of steps, we are actually following the score function, the score direction that leads us to the distribution over natural data, right? So, but with any topic, and I think all of us who have worked in different domains know, once something is powerful, there will always be equivalent perspective, right? And there are multiple others you can think of. You can also think of diffusion models as hierarchical VAEs with a fixed encoders. Of course, there are the other perspective from flow-based modeling, which leads to other class of models like flow matching and stochastic interpolants, but they really fit within a big family of diffusion. And one point that I want to bring out here, that one of the first papers that introduced the notion of diffusion was inspired by non-equilibrium thermodynamics, which tells us that already the ideas from scientific thinking, natural sciences, physics has led to where we are. Of course, maybe a lot of algorithm development doesn't happen directly from this route now, but really the first paper that introduced this idea came from non-equilibrium thermodynamics, right? But one big use case of generative modeling is not to just generate any sample, but generate samples with certain characteristics we care about, right? So this is, in fact, one of the big reasons why diffusion models are all over the place in so many different domains, is that they allow this very excellent controllability, much more better than the other model families, which to guide towards the characteristics that we want. So in this case, I'm showing you the simple figure where I am just by adding this very simple guidance strength parameter, which is a simple weight parameter here, I can move a data diffusion model over images of dogs to the specific dog species, right? And of course, there are lots of use cases of conditioning in sciences as well. But before I go there, I do want to make a meta point here. I'm showing you these images and distributions or diffusion models over images, and it is very intuitive for us to see what is happening here. But that also points out that in sciences, the evaluation itself is a very non-trivial task, right? If I show, for example, that there are two big use cases here, but there are lots of others, right? If I showed you that what is happening with conditioning of proteins, most of us non-experts would not be able to understand. So evaluation, which we take for granted in vision and language, is a non-trivial task as well. But coming back to the point that conditioning has many use cases in sciences, right? We can, for example, we might want to generate proteins with conditioning on a fixed motif, different backbones we might want to generate. In the case of climate modeling, weather modeling, given some coarse observations, maybe we want to do downsampling, right? And generally inverse problems, which are all the time there in sciences where we have some noisy observations and we want to get the clean observations from, right? So conditioning is very, very important for us. Another way which we can use already trained diffusion models. So now I'm talking about once you have trained your diffusion models, how you can use them is this new aspect of test time search. Which means I showed you that, okay, you can start from this sample from a simple Gaussian distribution and apply this denoising operation multiple times, but you can also expand this search in a tree-based manner to spend more compute during test time. So for one example is, at each step, we generate multiple samples. And we can continue and generate, let's say, n parallel samples and pick the one which fits our setting the best. Right? So let's say we want to generate proteins, and we can generate multiple proteins and pick the one which is relevant, which maybe satisfies some scientific criteria, right? And this is a new axis of improvement for these models, which has become very popular in last 6 months or so, because typically we think of improving modeling is during training, where we collect more data, optimize better, and get good results. But now, even with trained foundation models and diffusion models here, we can get better performance by increasing the amount of inference time compute that we spend. And really, we can think of this as like a general tree search procedure. And this is something that people in AI always love, right? Like we like to create tree search ideas. And in fact, it is very related to the notion of what are called as anytime algorithms. Anytime algorithms have been widely studied in planning and AI quite a bit, that you spend more computational resources to get better performance. But this is another way how diffusion models are being used quite a bit, right? So now, towards the end of discussion about diffusion models, I want to talk about one particular application from sciences about material generation and how scientific knowledge already has to be encoded to make this work, right? So materials, all of us would agree that they are very central to society. They have lots of use cases, but representing materials is quite a non-trivial task. And because they are complex periodic arrangement of atoms in 3D spaces, and we need to encode at least three, in the most common representation, we need to encode the atom types, the position of the atoms, and the periodic unit cell in which they exist. And what are the challenges if I want to use standard diffusion here? There are multiple. Materials is mixed data, which means atoms times is discrete and coordinates are continuous, right? So standard Gaussian diffusion will not work here, right? Materials have periodicity, right? Atom coordinates wrap around. So topology is no more Euclidean. It's probably a torus, right? Then the lattice vectors are invariant to rotation. So there is symmetry, right? So there is no more simple consideration. And of course, they are variable input size. So already, just to give an example of from one paper, this Matrogen, which was released by Microsoft, and of course, Elad here has done lots of new work using better models as well, is that to incorporate these different characteristics and challenges for materials, we need to come up with custom designed diffusion models. So that we need to come up with discrete diffusion. One example of that is mass discrete diffusion. For coordinates, I have to now use a wrapped normal distribution instead of a standard Gaussian distribution. The physical symmetries, the architecture needs to take into account, so we have to use an equivariant graphing. And even more importantly, which is sometimes very rarely discussed, is that the data, which is sort of central to all of generative modeling, all of AI, has been curated over lots of years from scientific expertise and lots of effort by community, right? So this is already an example of incorporating lots of scientific knowledge and large body of multiple years of works of scientific expertise to create a domain-specific generative model. And we'll hear today that even now we are still not there. So there is not more work to be done. And so this was mostly a description of diffusion models. I tend to think of generative models, different families of generative models like GANs, VAEs, autoregressive, diffusion, falling in different trade-off along few characteristics that we care about, right? And these are listed here, some of which you can already probably understand very easily, right? We want to generate high quality samples. It would be great if they are also very fast to generate on my computer, right? It would be great if I can guide them towards desired properties. It will be also nice if I can estimate the likelihood or let's say probability of a sample, right? Because, for example, in biology, people have been building probability models for a long time, and they know sometimes it has been seen that the likelihood of a protein sequence is related to some function, some property we care about, right? And so diffusion models characterization is here. I'm not going to belabor some of these. These are slides which are there. These are also covered in our previous tutorial. But really, that diffusion models are very popular because of two big things. They provide high quality samples, and they are much more highly controllable compared to other classes. Right? The other family that all of us use every day are autoregressive models, of which GPTs is probably the most popular example, right? Here also, you can in fact think of GPTs as also doing iterative refinement, but dimension-wise, right, at a unit-wise. So you take your sequence and you convert you use the standard probability chain rule, to convert your distribution into this one-dimensional distribution conditioned on the previous one. So there is this iterative refinement idea again, but at a dimension level, at a single unit level, at a single token. Right? These are the characteristics of GPTs. We know a lot about them, so I'm not going to focus a lot on them. But there is a summary here. And I think as last time I mentioned as well, that this summary is not a universal characterization. Of course, lots of us are working actively on these directions. And also, for every application, there are some characteristics which are more important, right? Maybe in some cases, we really don't care about cost of generating samples, and it's just the high quality that we care, right? I think that we should keep in mind. So that is what I just discussed till now is really about what are some objectives that we can use to come up with these generative models, right? But that is not the only ingredient. There are other ingredients as well, especially when you commit to, let's say, training a large diffusion model for multiple weeks or months, then you have to be sure that your training will lead to good results. And this has been one aspect of deep learning, which has been very, very powerful and nice, that we see more and more in multiple domains that the test performance of deep learning models improves very predictably. So it allows us to predict, okay, how my training will look like. And of course, it is predictable in data and model size and compute. And I'm not going to, it's very important that training large-scale distributed systems, some of the people who work on systems know is very challenging, but I'm going to focus on one aspect, which is the data aspect, right? I think, especially for all of us who are working on these things now, I think we have to move beyond this point that, okay, there is just some data sitting, I download it, and my model, right? There is a large effort, even in the commercial systems that you see, in curating the data, in figuring out the right mixture of data, the right set of diversity in the data, right? As an example here, most language models is not just Reddit or, one thing, right? They include the right mixture of GitHub code, right mixture of Stack Overflow, right? So this is data curation is in fact very, very central to most generative models. And that is why it has led to significant interest in this research direction of data-centric AI. And I think one point that came to my mind was that, of course, data diversity matters quite a bit, but some of you might already be thinking that the carefully formalizing the notion of diversity is completely non-trivial. But there are some scientific domains like ecology, for example, who try to do this, like biodiversity. We have to characterize biodiversity somehow, right? So I think studying notions of diversity from there could be very, very relevant for this data-centric AI, right? So really the general recipe of what we see today of modern Gen AI is combination of better algorithms and the right way of scaling by figuring out the right mixture of data. And of course, with this, now there are lots of new capabilities which have been enabled. We can generate new instances of high-dimensional data, which is very important for sciences, let's say generating new proteins and materials, right? We can guide towards certain properties that we care about. And very importantly, this is what leads to the next point that I will mention, that now in sciences that we know that there is this long tail of tasks, and most of these tasks come with their specialized data. And building custom models for each of these separate tasks has always been very challenging because of the lack of data. But Gen AI enables us to create this foundation or prior from which now we can then fine tune for the downstream tasks that we care about. So one way of updating our model for downstream tasks is just to update the parameters of the model. But a very important characteristic of recent Gen AI models, which will also lead to another important capability of these systems, is in context. So this is where really seeing in last few years that even without updating the parameters of the networks, by passing inputs in the context itself, right? Sometimes these models tend to learn a task, right? And this is really, as an example, a popular example of this from GPT-3 is translation. And provided the examples of translation, it learns how to translate just from context without updating the parameters. And this is the capability that will enable agentic AI systems, which I will talk about. And all of this together, right, has led to this moment in machine learning and AI of foundation models, right? classic machine learning and AI was very much specific, very much driven by developing custom bespoke models for every task we care about. Now we are more and more in this era where we train large foundation models driven by objectives of generative modeling, large data set, which leads us to this paradigm. Then we can fine tune them for any specific task that we have, and also enabled by this in-context learning. So now, so this was really a summary of where we are in terms of advances in Gen AI, of course, focusing a lot more on diffusion models. And now what I'm going to talk about is something which is very close to what I work on, and that till now what I've discussed is really learning with passively collected data, right? Which means, yes, we curate the data and we figure out the right mixture, but still it's one data which is collected by somebody, and then we go ahead and train them. But as you all know, that really we want to use these systems to make interventions in the real world, which experiment to run, which control input to use, right? So that's why we have to figure out a framework that will also allow us to learn to achieve goals by interacting with them. And that's the framework of reinforcement learning, right? A small introduction of reinforcement learning. So reinforcement learning is really formalizing this notion of learning by acting in the world. So here we think of the problem setup is very commonly this, that we think of our machine learning system now as an agent because it has agency to take actions in the world, right? It exists in some environment with some state. It can take actions in that state, and the environment gives some rewards for that action in the. And the goal of this agent is to figure out how to make the optimal sequence of actions to maximize the sum of rewards. And the problems, there are lots of problems that can be formulated under this general setup, and such problems typically we call as sequential decision-making problems, because the agent has to decide which actions to take. So beyond learning itself, now there is this other challenge of exploration. So the agent also has to figure out, the system also has to figure out which regions should I explore, which will be useful for my decision-making, and which regions should I quickly discard, which are not useful. So exploration is a central challenge beyond learning that arise in reinforcement learning, right? And just to emphasize that how important this has been in recent advances is this is a probably all of you, some of you have taken my courses or otherwise have seen me describing this, that, okay, how did we go from GPT to ChatGPT? The GPT-3 paper comes around May 2020, academic, CS people are interested, nice thing, but I'm pretty sure none of the people outside were really that much into AI back then. But ChatGPT launches in November, and everybody is talking about AI. So what is happening in these two? Really, what is happening is reinforcement learning from feedback, a major component what was. Where what we do is we use our language model as an agent with the goal that it should generate responses which will be preferred by humans. The base GPT model has no incentive. It can just continue. It has incentive to generate correct, grammatically correct sentences. But for a prompt that you give, an instruction that you give, to respond exactly to that so that you are satisfied, there is no incentive in there, right? So reinforcement learning from human feedback was really that these language models was trained with reinforcement learning, where they generated responses, which was annotated by lots of human experts, actually. This is, again, a question about data and data annotation, right? Where lots of people annotated their preference of their responses, and this is how they were trained. And in fact, some of the quirks that we see of ChatGPT and other comes really from this, right? In the beginning, ChatGPT used to, or other generative models used to reply in lots of smileys and all. That was because people used to just prefer that, or lists. People prefer lists, right? So it was all driven by reinforcement learning from human feedback. Recently, of course, in last 1 year, a big class of models which have become popular are so-called reasoning models, these are really, again, language models trained with reinforcement learning for tasks from math or coding domains where we have a computational verifier, which means, for example, if you can take these math word problems or programming problems, the language model generates an answer, and we have a verifier, which, for example, in the math word problem cases, whether this answer that it was generated is correct or not. In the programming case, it could be unit tests that we write, right? And the language model is trained to generate more and more responses that passes these computational verifiers. But really the big, and this has led to these famous family of models, I think all of us here and know about. But the question for us today, of course, is that can youth-inspired science and engineering problems lead to new development of parallel ideas? And I think it can, because of lots of new challenges that arise in scientific domains, which is not there even in, let's say, math and coding, which also is a form, right? So let me list down some of them here, right? As I just described a couple of slides ago, right? Even the so-called reasoning models are driven by this need of a computational verifier, which is very cheap, which I can write on a computer and done, right? But most things we want to do in for scientific and engineering domains, let's say if you want to explore design space to figure out the best material, best protein, or best molecule, right? These are really driven by very expensive rewards like wet lab experiments, right? Or even simulations are typically much more longer running than just checking a unit test. It's fractions of a setting, right? Uh, Similarly, even if we have simpler, let's say, cheaper rewards, many problems in scientific domains require us to make long horizon decisions. For example, in agriculture, farmers make decisions, but the horizon of even if you provide some intermediate reward, the final thing that we care about is the yield of, let's say, their decision strategy, which is maybe months or years. Right? In the other challenge is non-stationarity, which is really very understudied even now, which means, for example, we know we can build lots of, let's say, models for hydrology and other domains, but there is human feedback involved, which changes the future trajectory of, let's say, our model. So how do we incorporate human feedback in our decision making, right? Always, I've never faced a problem in scientific engineering domain where we care about only single reward or single objective. There are always multiple rewards, multiple objectives, right? We want to design drugs which are good, molecules which are good as drugs, but also safer, right? They're always constrained, right? And also, in many domains, as I mentioned, the one challenge of reinforcement learning is exploration. Just unbounded exploration is not even feasible. In fact, unethical sometimes, right? In healthcare and clinical trials, as some of us know. So I'm going to talk about one framework, which is at least, which I believe is a very good candidate for solving some of these problems, especially the first one, which is what I developed in my lab, which is this idea of adaptive experimental design. So really the idea, big picture idea here is this, that when we build our model, we should quantify uncertainty in our prediction. And then we can use this uncertainty in our predictions to reason about the information value of action. And why this is useful? Because once I can reason about how valuable a particular action will be to my future goal, then I can intelligently explore the space while minimizing the actual real world results, right? And I will give you a couple of examples of how this framework has already been used for real world applications with lab in the loop, like actual real experiments on 2-3 domains. For example, one work that we did recently is this adaptive experimental design for additive manufacturing, where we paired up with experts from additive manufacturing and trying to generate these metal alloys, particularly this GR corp, which is used for aerospace and biomedical applications. And again, the candidates that were generated, the one thing I want to emphasize here is by this system were actually evaluated in the lab. So there is a lab in the loop. An expert goes and do the experiments in the loop to figure out the best metal configuration of the 3D printing to print this metal alloy. And for the first time on the right-hand side, we can see that this was an open problem in the field. For the first time, we were able to successfully generate structures of this model in a lab under this laser power budget of 10,000 watt, 1,000 watts. And this was done only by using 50 evaluations out of, let's say, millions of possible configurations. And of course, it included, there are lots of details in the paper, it included lots of domain knowledge from the scientists to figure out the right search space and the constraint. Right? We've also used it for materials discovery. Here we are talking about porous molecular materials, like porous materials. So this is an example of covalent organic frameworks, which are one type of nanoporous materials, and they can be useful for, because they are porous, they can store lots of gases. So gas absorption and gas exchange is a very big application for these systems. Here we looked at, can we store natural gas? Natural gas is a bridge fuel going from gasoline to hydrogen. And again, out of 70 to 80,000 possible cops, this framework could figure out the best one in just less than 0.3 evaluation. Recently, as a meta application, we've also used it for steering language models, right? When we use language models, especially the most recent and the fancy one, that's the reasoning one, they cost a lot of money in APIs, right? And they also take a lot of time. So we looked at one particular example, but I think this is a very general application of guiding these language models with this framework to improve their accuracy and also calibration. And there are many more, and please feel free to use this QR code to find out more about this in electronic design automation. For example, we've used it for multiple objectives, multiple constraints, optimization of discrete and mixed design spaces, multiple fidelities. And that is why I believe this is really a very promising direction for agents to explore design space. Now, towards the end of my talk, I'm going to talk about two more buzzwords, which are really never been in buzzwords in AI, which is, if I'm talking about naturally point that we can think of, if I'm talking about that acting in the real world is hard, right? And this is some of my colleagues in robotics and geosciences and other domains have always realized, then we should think about building simulator or computational systems that will allow us to act in the digital world and figure out to take my actions carefully, to plan about my actions. And that is the idea of world models, right? World models have always been around in AI as this thing that we want to learn transition or dynamics models of a system, right? Why they are called world models now is one primarily big use case or application in which they are studied is this video generating models. And we think of, let's say, self-driving cars, which exist in the real world and it's generating future trajectories of the world. But very simple definition of world model is this. I think there is a lot of confusion about definition of world model, but it's a very simple definition. It tells me, given a state and an action, what will be the next state? And I'm using the word belief state because all of us know, not everything that has been seen in the past has to be incorporated in the state, right? It just needs to be the right succinct information that is useful for future prediction, right? So why are world models popular and being talked about quite a bit? Because they let us roll out future trajectories under candidate action, right? And what does this allow? This allows me to do planning, right? Now I can try counterfactual actions digitally in these computational neural models and see the future trajectories, how they look like, and then take my action. So this will lead us going from reactive agents, whatever I've described before this, are reactive agents. They come in a state and immediately take an action. But we know even from real life that there are some scenarios where we have to plan, we have to think a little bit, right? So that's what world model will allow us. So that's about world models. And then, of course, probably the biggest buzzword of around us, which is agentic AI. I think for maybe for non-CS people, I do want to emphasize that when we study AI, we've always been wanting to build agents. In fact, the famous AI book, Norwich and Russell, the first chapter is about agents. So agents have not been surprising to us, but it seems like when I discuss quite a bit that this is a new thing which is coming up. One thing is definitely new, which I emphasized last in my description of foundation model, is that now with in-context learning, especially for language models, I do not even need to update the parameters to learn a new term. And that allows us for me to deploy these systems in scenarios where there is no need for the model to be updated with the parameters and can just learn by interaction in the in-context, right? And because the capabilities, two big capabilities the modern foundation models, especially the language models have, which they are really good at, is language and coding, right? Think of programming as one form of language. And that allows us universal specification of actions. What I mean by that is, in all the previous settings that we used to study, the action space was manually described by a human, like an expert, like a CS person. But as you can imagine, manually specifying it is always going to be slightly limited. But natural language and programming just allows the universal specification. If you can write a code, you can call by API any software that you like, right? And that is why this term has become more popular of agentic AI, because now by using generating code, you can call any software. So the action space just becomes universal. And we are seeing lots of applications of these things, right? Some of us use this, right? One of them, big one, is literature search. Some of these agents can now do a lot more semantic literature search look at a lot more papers and tell us. There are lots of AI co-scientists being developed, which are really generating these high-level hypotheses for us, right? And there are lots of course, like coding agents and others that we use all the time. And again, big challenge here becomes how do we make sure that we work nicely with scientific systems where, again, rewards for working in those systems is important. So this is where I will stop, where there is a lot more described in the report as well, and you can happy to take any questions towards the end. But I think Anuj, we will go through the third part and then we can take some questions towards.